Okay. pH over here. Amount of base added here. Okay. What can you tell me about this acid just from this shape? It's what? That might be an assumption, but this isn't really a cliff face. It's just kind of a hill. Okay. It is in fact weak. Okay. This kind of shape is what you get when you get a weak acid. Okay. And this region right in here is that buffering region we talked about from Monday. Okay. This is the area where it's hard to get the pH to change. Okay. So this becomes a buffer for you if you want a buffer. Okay. But this is a weak acid because it looks like it never really got down to 0. Alright? Never really got there. So this is an indication we have a weak acid. Alright, never really got down to 0. And so if this is not a cliff face, how many cliff faces does it have? 1. So if it has 1 cliff face, what kind of acid is it? Monoprotic. Okay. And then what we want to do is to find the steepest place on the cliff face. The steepest place on the cliff face, whatever that is, that's the equivalence point. So we would identify this equivalence point right here. That'd be the amount of the equivalence point, or the value of the equivalence point. Okay, and down here is the volume of base used. The acid we used on Monday might look something like this, the weak acid from Monday. Oops, that's just one hydrogen. High H, CH3, CO2. Okay, and we were putting KO8 solution in it to neutralize it. So the proton here came off, joined up with the hydroxide here. And so we're making water. Whoops, that's supposed to be an arrow. And we've got freed potassiums and freed acetate ions. And when the number of these hydrogen ions from the acid is equal to the number of hydroxide ions from the base, we reach the equivalency. Got it? That make sense? Any questions about that? Not hearing any. Let's move on. I'm not aware of any strong triprotic acids, but there are a number of weak triprotic acids. Let's look at one of those.
Are there any weak diprotic acids?
What?
Weak diprotic acids?
Yeah. You want to look at one of those first?
No. I assume it's just the same as the other one.
It's kind of the same stuff.
Slightly higher.
Yeah. So here's a How many cliff faces? 3. What kind of acid is it then? Well, that's not the fact there's 3 cliff faces doesn't mean it's weak. Okay, got it. So this, because it doesn't look like it's going to ever get to 0 or close to it, then that's what we can identify then as weak. But it's the 3 different cliff faces and the 3 different equivalence points then that makes us know what? Triprotic. Protons being removed from the acids. An example might be phosphorus acid. And so as we add more base to the solution, I'm going to use potassium hydroxide again. The hydrogen ions are leaving one at a time, and the hydroxides are leaving all at one time. Okay, they become boyfriend and girlfriend. The result is that we're going to make water. We're going to have the freed up potassium ions, and we're going to have freed up what is left from this acid over here on the left. We take one proton off, it's got to have H2PO3, and what else to show the complete species? 1 negative. Take one proton off, we get 1 negative. Okay?
The number of hydrogens, does that determine if it's triprotic, or does that...
Generally speaking, we put the acid hydrogens on the front of the formula, usually.
But does that determine if it's triprotic, diprotic?
That's generally how you know it's triprotic, diprotic. And it depends on the way it's written and how. If you're writing, a lot of the organic acids are more complex, and so sometimes, depending on who's writing the formula, the hydrogen won't show up on the front. Okay? But anyway, so this is the first dissociation. Okay? Can you write the second dissociation now? Have you got enough information now to write a second dissociation? Try it and see. See if you can show me how we get to that second equivalence point. We're going to climb up the rest of this cliff and get to the second cliff face.